Okay, so let's get right into it. If you've spent any time at all in the tech world, you've probably heard the doomsday prophecy, right? This ticking clock they call Q-Day. The supposed moment a quantum computer fires up and just shatters the entire internet. But how much of that is actual science and how much is just, sci-fi hype?
I mean, that's the billion-dollar question, isn't it? Will this crazy new type of computer really just crack the whole digital world wide open, leaving everything from your bank account to your DMs completely exposed? It's a totally fair question, and today we're going to pull back the curtain and look at the reality behind the panic.
You see the headlines everywhere. You hear the panic. And look, it makes for great clickbait, it's a fantastic movie plot, but when you actually look at the physics of it all, the story gets a lot more interesting. To really get why, we first have to understand how all your stuff is protected right now. So let's dismantle this whole narrative piece by piece. First things first, to understand the threat, you've got to understand the lock it's trying to pick. Modern cybersecurity isn't just a password. It's this brilliant piece of mathematical architecture that's basically a one-way street. It's super easy to go in one direction, but nearly impossible to turn around and go back. And most of the time, that architecture is called RSA encryption. It's the standard. It protects your emails, your bank login, pretty much everything you do online. And its real strength doesn't come from some complicated secret, but from a very, very simple math problem that happens to be incredibly hard to solve.
And this is it. This is the core of the whole thing. To create a digital lock, you take two gigantic prime numbers, we'll call them P and Q, and you just multiply them together. The result is an even more gigantic number, N. That N is your public key. Anyone can see it. But the original ingredients, P and Q, those are your private key. And here is that one-way street in action. Multiplying P and Q together? A computer can do that in a flash. It's trivial. But if you only have the answer N, and you try to work backward to figure out what two primes made it, well, for a normal computer, that is an absolute brute force nightmare.
So just how much of a nightmare are we talking about? Get this. If you took every single supercomputer on planet Earth, linked them all together, and set them to work on cracking one single modern encryption key, it would take them about 300 trillion years. Yeah, that's the bottleneck. That's why your data is safe. For something to break this, it would have to completely change the rules of the game. Which of course brings us to the key, the theoretical skeleton key that promises to pick this supposedly unpickable lock, the quantum computer. And this thing, well, it doesn't play by the same rules at all. See, your laptop, your phone, they think in bits. And a bit is always in one of two states. It's either a 0 or a 1. Simple, like a light switch. A quantum computer uses something called a qubit. And thanks to a wild quantum property called superposition, a qubit can be a 0 and a 1 at the exact same time. It exists in a state of probability, letting it explore tons of possibilities all at once. Now, back in 1994, a mathematician named Peter Shor came up with an algorithm specifically designed to run on one of these quantum machines. And Shor's algorithm is basically the mathematical nuke. It uses that weirdness of superposition to find those two secret prime numbers, turning a 300 trillion year problem into something that could take just a few hours. And here it is. This is the major plot twist in our story. On a whiteboard, the math is perfect. It's elegant. It is undeniable. But trying to actually build a machine that can run that math, that's where you slam headfirst into a wall. And that wall is called physics. So let's leave the clean, tidy world of theory and get our hands dirty in the messy, brutal reality of building one of these things. This is where we meet the real hero of our story today, Mother Nature's built-in firewall.
I mean, think about it. If the math has been around since 1994, and it's so powerful, where's the machine? Why aren't all of our bank accounts being drained as we speak? The problem isn't a flaw in the math. It's a fundamental flaw in, well, the universe.
Okay, so meet the ultimate party pooper, quantum decoherence. That magical superposition state that makes a qubit so powerful, it's also unbelievably fragile. The instant, and I mean the instant, a qubit interacts with the outside world in any way, boom, it collapses. It forgets it was a 0 and a 1 and just becomes a boring old 0 or 1, and the entire quantum calculation is completely destroyed.
And what can destroy it? Oh, pretty much everything. A stray particle of light bumping into it. The tiny vibration from a truck driving a mile down the road. A temperature fluctuation of a fraction of a degree. Anything. Qubits have to be more isolated from the universe than basically anything humanity has ever tried to build before.
They are the most delicate things imaginable.
Now, because these physical qubits are so ridiculously fragile, scientists can't just rely on one. To get a single, stable, usable qubit, they call it a logical qubit, they have to bundle about 1,000 physical qubits together. The other 999 are basically acting as bodyguards, constantly working to protect and correct errors for that one central qubit, shielding it from that dreaded decoherence.
So let's just do the math on that. To run Shor's algorithm on a single standard bank key, you need a couple thousand of those logical qubits, which means you need a machine with millions of physical qubits, all perfectly isolated, all working in perfect harmony. And right now, the world's most advanced quantum computers have like a few hundred, and they are incredibly noisy and full of errors. So this is the real takeaway. The problem has totally shifted. We are no longer bottlenecked by the math, we are fundamentally bottlenecked by the physics and the engineering. We have the blueprint for the skeleton key, but we are miles away from even figuring out how to forge the metal to make it.
And here's the final twist. The cybersecurity world isn't just sitting around, waiting for the sky to fall. Researchers are already designing and even deploying brand new kinds of encryption called post-quantum cryptography. These are basically new locks designed to be tough enough to withstand attacks from both classical and quantum computers. The arms race is already well underway.
So what's the big lesson here? The world becomes a whole lot less scary when you understand the real variables at play. The quantum threat is a real theoretical possibility, but it's a distant, monumental engineering problem, not some doomsday event happening tomorrow. So instead of falling for the hype, let's learn the variables. Let's respect the physics.